Now, of course, errors can happen anywhere, right? We all share this problem. And we all want reliable programs. And we have absolutely no time to handle errors because we have other more important things to do. So what do we do? Before we go into the details, let's first see where errors occur, how they occur in the program. Say you have an operation like this one where you open a file, and now what happens if the file doesn't exist? Well, how could you get an error out of this expression? Well, if you have old-fashioned functions, you could just have a return value, and you would have to check the return value. Of course, that doesn't work if you have constructors because they don't have any return value. So you can revert to something like out parameters. It's still not particularly pretty. You still have to check them manually. Now with newer C++ versions, we have no discard. That are status bits. So the idea is that whenever something goes wrong, the system internally would just, this object will just set a flag, and you can just continue running your operations, and only at the very end you would actually verify whether things worked or not. This is of course fine if checking at the very end is good enough, if you don't need any intermediate results, like when you're writing to a file. It's also very common actually when you're dealing with graphics cards, when you are doing graphics output. There you're also just executing the command, you're rendering through triangles, and at the very end you may ask the question, well, is now my graphics card, my surface lost, and I have to do something. If you need intermediate results, like when you read the file, well, that doesn't work so well. This is actually the default for C++ IO streams, which are still part of the C++ standard, even if now, with the format, they are not as popular anymore as they used to be. Another idea that kind of goes along the same idea of having a single control path, where you can just basically have one path through your program, regardless whether you have an error or not, are monads. So what they are essentially is it's a variant of whatever the result is and some error state. And you would either pass the result or the error state through the program, and together with some utilities, you can then manipulate these objects. You can say, okay, I'm just going to do something on the result, but if you're already in an error state, just carry on. Just keep this,
change your budget.
Just move this error out of the program, and you're not going to actually process it any further.
Okay, sorry.
All right. Something like that will actually come our way. There's a proposal making its way through the C++ Standard Committee. That's the PO 323. It's right now at R11, so it's revision 11. So it has gone through many revisions already. And I think it's working its way to standardization. So I think on C++ 23, we'll probably get it. Of course, then there are exceptions, which are the standard way nowadays to produce or to emit errors. There are a few caveats with exceptions that I want to briefly talk about. You may already know them, so you should not catch exceptions by value, because then you get slicing. That means that if essentially you have a structure B that's an exception and it's deriving from a structure A, if you now catch A by value, two things are happening. First of all, you're losing everything that B added to the A, which for polymorphic objects, that's usually not what you want. And you are invoking some sort of copy, and that copy itself may fail, and then you have a double throw, and that immediately terminates your program. So you always want to catch things by exception. One thing that I find interesting is if you're just writing a throw with a semicolon, that actually throws the original exception. So even if you're catching by value, it doesn't throw A there, it actually throws the original B. Kind of a curious side thing. All right. What's wrong with exceptions? Well, you could argue they're kind of like multi-level go-tos. They're almost as bad. And the reason is that they're adding many of these code paths in your code that you have to test against. And that's actually one reason that some code bases don't allow them. So if you have like a function like that one, you have a throw statement in the increment function, and then it's called down here in the main. Then effectively, what you have here, effectively, if you could say this is a bunch of gotos. It looks like this, right? So if you throw an exception, you kind of transport this exception out. You're setting some exception somewhere in your environment, and then you go to this extra exception escape hatch from your function, and you pop out somewhere, and wherever you pop out, you will then again have this kind of goto where suddenly your control flow goes to completely somewhere else, your catch clause, and that's it adds complexity to your code. Now, of course, some of you may say, well, stop whining. We have to write exception-safe code. So, first of all, what is exception-safe code? Now, it's not really specific to exceptions. It's a general failure-safe code. There are several levels of guarantee you can give for a function. The best one you can give is that it never fails. That's nice, but it's not always achievable. The next one is the strong exception or failure guarantee, that whenever a failure occurs, the function guarantees that the state of the program is going to be whatever the state was before you call the function. So your failed function is effectively a no-op. That's certainly possible and very desirable to do in library functions, and the standard library in general does it. It's very hard in application code, because once you start changing the state of your program, you may have made many changes, and then after a while you discover, oh shit, something's going wrong here. And then you would have to write code that rolls back all these changes, and you may have to remember all these things on the way coming, so that you can roll them back on the way back. And all that effort and all that complexity is really just because you have to cope with this error. And that's annoying. And then there is the basic exception guarantee. That's much easier. And maybe that's good. So the function, if it fails, it won't restore to the state that it was in when you call the function. Instead, it will just be some valid state. Now, you can imagine we have a support call, right? Pretend to be Microsoft. Get a support call. Hello, this is Microsoft Word support. Writing a book, and suddenly Word deleted everything. And the answer is, well, Word only provides the basic exception guarantee, and an empty book, that's a valid state. And the customer says, yeah, thank you very much. That's a great piece of information. I really love this program. Thank you. Probably very unlikely that you're going to have this discussion. So I would say that basic exception guarantee is pretty useless. Now, here's the challenge. Error handling is a lot of effort. In development, we must be really paranoid. And it creates a lot of extra code to handle all these potential errors. And then in testing, we have many code paths to test because we have all these error conditions. We have to test them all. Otherwise, as we know, if something's not tested, it won't work. And then at the end, we have very little customer gain because the customer doesn't pay us to handle errors in a great way. The customer pays us to solve problems. So, what do we do? That was the question we had, and I want to tell you what we did. So here's what we did. First of all, check everything. So for every API call you make, there is a special wrapper that you write around the API call, making sure that that API call works. There are different ways to produce errors. There are get lost error in Windows. There's H results. On Unix, you have Arno. So you have different wrappers. You use the appropriate one. Every API call gets checked. All the assertions that you added to the program, and you add plenty of them, they stay in release. You will still check the program whenever it's running. While it's running on the customer machine, it will check itself. And these asserts are aggressive. You want to write them in as strongly as you can, so that you are not timid about it. We write, and that's a contentious one, we write no except into all the functions that are not designed to throw exceptions. The argument is that if an exception does come out of these functions, the program is going to misbehave anyway. And if you write no except, the program will terminate, but we can set a handler with the set terminate in C++, and we will get information about the termination. We will know if something went wrong, and we will know early. We will know close to the function that actually threw the exception, because they are all marked no except. And once we did all that, we built all these things, we checked everything, we asserted, and we brought no except in there, we do nothing. We assume everything works. Okay, well, what good does this do? The goal here is we want to keep the set of code paths small. We want to keep the program simple. We don't want to deal with this explosion of program states, because you have states in the program that just exist because certain things failed, or because you must assume they exist because certain things fail or could fail. You want to talk about a simple set of program states. You want to have a small set of code paths. So that's why we assume that everything works. So what do you do if the checks fail? Priority number one would be you collect, and that's priority number one. That's the most important thing. You collect as much information as possible, because we need to learn what the problem was. And that's more important than at that moment than to save the data of the customer. The customer may lose data and may be angry. Yes, but we have to fix the program so that this problem does not occur anymore. And then everyone else is happy. This one customer has to suffer for the common good. So priority one, we collect as much information as possible. When it's on a client machine, we send a report with a memory dump. We send it home for us to analyze. If you are in a server environment where you are controlling the server, you are even better off. You can actually stop the thread, and you can notify the operator, and then you basically have the best debugging environment that you can imagine. You can just attach to your server, and you have access to all the variables and all the state that you have in your program, and you can debug to your heart's desire. So that's what we do. Now, only priority two is you carry on somehow. If the check that failed was critical, so it was an assertion that you didn't assume would fail, if it's an API call that you didn't think would fail, from then on, the whole program behavior is undefined. You don't really know, you don't want to reason about the fallout of anything that went wrong. As long as an assertion, when it went wrong, when an assertion failed, then you don't really know how the program will behave in the future. Maybe some program state is corrupt. You don't want to do any reasoning. This is wasted effort to reason about what happened, how the program would be if the assertion failed. Assertions just don't fail. We assume they don't fail. So if they fail, the program behavior is undefined, and you don't send any further reports. We just disable the reporting mechanism. You don't want to know about this program anymore. But still, do not terminate when an assertion fails. Do not, because you want to encourage developers to write aggressive assertions. How do you encourage them? Well, at least you shouldn't penalize them if they write a wrong assertion. If they write an assertion that fires constantly, needlessly, then it should still be the program, the customer impact should be nothing. The program should work. Because otherwise, this poor developer who could just terminate the customer machine for no reason, next time won't write the assert anymore. You'll be like, oh, I'm afraid writing this. I don't want to do it. So you cannot terminate when an assertion fails. If you need extra safety on top, if you think, oh, I need to terminate, then add it at a higher level. Add it on top. Like if you have, we don't have a nuclear power plant at home, but we do have a server that stops that serves various types of requests. And what we do is we categorize these requests and count how many pending, outstanding requests we have per category. And if there's a problem, we stop the thread, but it may as well run into an infinite loop or something. At least this request doesn't come back to us. So, and if that happens frequently, then these bad requests will pile up, and at some point, it will fill out a quota, and then these requests won't be served anymore. But that doesn't mean that other requests won't be served. So maybe just part of the problem is part of the server is broken, and we have to fix it, but the other parts are still working and are still okay. So that's our way of providing at a higher level some sort of robustness. What do we do next? We have to reproduce the error. You cannot write meaningful error handling code if you haven't reproduced the error, because you may not really understand what the cause of the error is. You just have an error message, but what led to this error message? What's really the underlying cause? You don't really know if you haven't actually reproduced it, if you didn't really understand the problem. So only for the errors that are reproducible, you should write error handling code. And if you don't, then these error handlers may never be used, because you are handling an error that is not really, it's not, you think it's happening, but it may not be the actual cause of the problem. It may be something else that you overlooked. And at least the error handlers that you write will never be properly tested, because you cannot reproduce the situation where this error actually occurs in the wild if you have no reproduction. So you really need a reproduction. Of course, as always, 5% of the handlers handle 95% of the errors. So the point here is, focus on writing, if you don't have infinite resources, so you look at your reports of errors, and you write rather a few error handlers for the most popular errors, and focus on writing good error handling code, rather than mediocre error handling for a large number of errors. So the bad error handler is the message box. It's like, oh, an error occurred. Well, that doesn't help me. A good error handler would actually fix the problem. If you can fix the problem, that's exactly what you want, because then you have a no-fail function again. You handled that error internally, you fix the problem, you carry on. We had, for example, in the beginning of ThinkCell, we used the XML component of Microsoft, and we had reports, lots of them, that this thing doesn't work. We couldn't instantiate the XML component. And of course, yeah, you have to reproduce the error. So we could have written some sort of funky error handling code, popping up message boxes and whatever. But it turned out that what was broken in this case on these machines was actually the registry. So all we did is we just re-registered this component in the registry whenever you ran into this problem. And then we tried again. And lo and behold, the error disappeared. So all we really needed to do is, in this case, we were actually able to do something in the program that made the error completely disappear. And this is really the gist of it. This is the important thing that I want to get across. There you really gain. You gain reliability of your program. You don't just not crash. That's not enough. You just increase the reliability. You get your job done, and don't just pop up an error message box. I want to go with you through categories of errors that we identified in our experience, in our lifetime as a company. And there are a few ones, and they served us well, so I want to talk about them. Of course, one of them is the critical error, where the program is not designed to handle. Trivial ones would be you access a null pointer, but also API calls that shouldn't fail. Presumably, you did this API call for a reason. So and if you said it must not fail, then it shouldn't fail. It's a critical error. So if the assertions fail, that's also a critical problem. We deal with them, as I said, as if they never happen. So that means they don't have any handler. We don't write a single line of code that is dealing with such failures. Anyone who tells me in a code review, oh, I put this in just in case. No, there's no just in case. These things don't happen. Otherwise, your code gets more complicated, and we are striving for simple code. So we just define that these things are not ever happening. And afterwards, the program behavior is invalid. Now, what do you do when these things fail? Well, as I said, you send an error report and you disable future reports. Your program state is invalid, so you're just not, the program is not talking to you anymore. You don't want to hear about it. With a server, you can halt the thread and you wait for someone to attach a debugger to find out what's wrong. Now, here it's important, again, you only bother the user if you're really sure that something is going wrong, will go wrong in the future. This does not hold for assertions. Someone may have written a bad assertion, a too aggressive assertion. It does happen frequently. I would say maybe a quarter of all assertions are that category. And you don't want to pop up something to the user that says, "Oh, alarm, alarm," if really just it's something that you could have just ignored, right? It's still a bug though. You have to fix it. If by removing the assert, because you understand that this assert is too aggressive. Here's another category, the kind of the untested category. These are things that you want to know about when they happen in your program, in particular because you could never reproduce them. In your lab, they never occurred, but you do have you do know that they could happen. They're documented to happen, but you've just never seen them. Say here you have a register foo, okay, and in your program, and or in the operating system you have a register foo, and we hook it. We just say, okay, the register foo function, we want to know about everything that goes through this register foo, and we put in a hook. Now, first we call the original register foo, and then if that register foo succeeds, we keep track of that for ourselves as well. Because we want to know about all foos. Now, it could very well be that if you put in an invalid foo, that this register foo fails. And you can reproduce that. You can just write code that says register foo with some invalid foo, and register foo fails. Okay, so we can reproduce the problem. But maybe in the target environment where you have this register foo, this never occurred. Never ever did someone give you a bad foo. If someone would, you know how to react. You probably don't want to keep track of things where the registration failed. So you could say, well, it's all fine. Well, the thing is, you don't really know why you got an invalid foo. Maybe something else in the environment was wrong. Maybe you want to understand better why you got an invalid foo, especially if you never got it. So that's the thing where we actually we want to know about it. And the way we do this is we also send reports for these cases. We don't stop reports in the future because the program is basically still in a valid state. The thing is, you have to watch out that these things may be called quite often because you may run into the situation, every 1,000 times a second. And so there has to be some throttling so that you don't overwhelm the network connection with your error reports, and the program is busy doing nothing else but sending error reports. In debug, of course, you can notify the developer. You can say, hey, I just found a reproduction for something that you've never seen before. So I'll let you know. Now you have something to work with. And the server just sends a report. It doesn't stop the thread. The other bugs, like the bad user experience. For example, PowerPoint sometimes makes shapes disappear because PowerPoint's buggy. We have an add-in for PowerPoint. That's our business. And maybe say PowerPoint actually has a problem. Shapes sometimes disappear, which they do. And we know about it. We can reproduce it. It's understood. But it could have, of course, be now that people call and say, hey, shapes suddenly disappeared. What's up? What's the problem? And if we are lazy and it only happens rarely, you may say, well, okay, I'm going to handle this error in my code. It's defined behavior, and anything that I can reproduce in the lab should really be defined behavior for my program. So it's supported, it has been tested, but you don't really want to put any more effort into it. So all you do in this case, because user may call now, and they say, hey, my shapes disappeared. What's up? And what we want is in this case, is to log. You want to write it somewhere where, in hindsight, your support guys can or girls can go and look at the logs and find out, okay, this user, she ran into this condition, and it's understandable that now these shapes disappeared. We understand the situation she ran into. There's another one of an indication of a broken environment. For example, you may have another add-in. As I said, we are working in PowerPoint. It's a PowerPoint add-in. And someone else, we hook functions. We hack into PowerPoint, hook functions. And some other add-in may do the same, and they hook the same function, which is usually fine. I mean, we support that. It's fine. We recognize the situation and we deal with it. But you don't know if the other add-in is ready to deal with it. So this still could be a cause of a problem. So what you want to do is to log it in general may actually fill the log file. But at least if you have someone looking in a remote session at this machine, you want to notify that's going to be your support personnel. They are looking at the machine in a remote support session. Then you want to notify them that something is weird about this machine. that we have an indication that something is non-standard. They should know, so you should at least log it, and then they could look at the log. Yeah, that was my list of categories of errors and how to react to them. What do we do for error analysis? A few things. So the reports are sent to our server as memory dumps. They are either sent automatically if the user allows, or if they don't allow, we prepare an email. So when they run into a problem, we prepare an email, and then the user can send us this email. And so that's that way we get to the same information. And this all goes into a big database that's available to the developers. They can open the memory dumps and can look at the problems. They are automatically categorized. They are automatically opened in a debugger, so in a command line like scripted debugger, and we find out where they occur. So they are categorized in the database, and then the developers can look at them. Now, one nice thing is we can mark errors as fixed. And that would trigger automatic updates. If we get an automatic error return, we actually write back, well, if you want to have this error fixed, update to this version, and they're automatically sent to the appropriate web page, or we just silently install the update if it's allowed. This also works for emails, so and that's kind of magic. You know, you get an email, and if that something is wrong, and you immediately bounce it back and say, if you want to have this problem solved, please update to this version. It's close to magic. The user just hits send, and then bling comes the answer. And it's like, please update to this version. I was like, wow, you have a really fast support department. We went one step further. So often the problem is related to the customer environment. Because usually if it's not related to customer environment, there's a good chance that your in-house testing is going to catch it. Because, well, they've done some testing. And very frequently there's another third-party add-in, it's a new add-in, it's a new version of an add-in, and then suddenly it starts causing problems. And it would be nice if we could just understand which add-in is causing the problem without actually any developer looking at it, right? Automatically, we could find out. How can we do that? Well, the memory dumps, they all have a list of loaded modules that are in the process. And these modules tell you a lot about the environment. They tell you which add-ins are being loaded, which versions of these add-ins are being loaded. So maybe you can make use of that information to find out which module is actually causing the problem. Okay, so we did this in a rather, we wouldn't be ThinkCell if we wouldn't have great fun doing this in a very statistically rigorous detail. And that's what we've done. And I'll tell you how our statistics look like and how we actually do this analysis. So the idea is you have a large database of problems, and let's pick out one problem out of that database. And here we have 12 problems, just as an example, and all the ones are the ones that have a particular problem. And you have modules associated with these dumps, and you say you have a module A that is contained in some of these reports, but it's among the ones that are this particular problem. This module A occurs 3 times out of 6. And the ones that don't have this particular problem, the module also occurs 3 times out of 6. You would think this is probably unrelated. Statistics say it's probably unrelated. Now you have another module, but it occurs 4 times out of 6 in the ones that actually have the problem, and only 2 times out of 6 in the ones that don't have the problem. I was like, maybe it's that module. Maybe it's at fault. How can we decide? Now, if that's responsible, or maybe it's just chance, the 4 times out of 6. How can we know? Here's the idea. Essentially what we want to do is we want to say module B is responsible. That would mean if module B is responsible, that probably the likelihood of running into the problem if module B is installed is much higher than the likelihood of running into the problem if module B is not installed. So the probability that the problem occurs is much higher if module B is there. It's lower if module B is not there. What we do is to compress the sequence of 0 and 1s up there. We write essentially a compressing algorithm. And we're just going to use a simply Laplacian estimator that over time, with each report that is actually compressing, each 0 or 1 that is compressing, it's going to learn about the statistics of how often this problem actually occurs. How many 1s, how many 0s you have. And then it turns out you have the number of bits that it takes to represent this sequence is, if you have 12 bits with 6 1s, then you need 13.55 bits. It's up there as a formula how to calculate the number of bits if you assume that Laplacian estimator. And this one estimate, the estimator assumes that the probabilities themselves are equally likely. So the probability P of being 0.1 is just as likely as the probability P being 0.9. And it tries to narrow down with the number of reports increasing. It tries to narrow down that probability. And then for 6 out of 12 bits being 1, you need 13.55 bits to compress. Not surprisingly, it's larger than the 12 bits because I mean no compressor compresses all kinds of data. What this will compress well is something where you have lots of 1s or lots of 0s. Now, in particular, if you have a 12 bits with no 1s at all, you only need 3.7 bits to represent that. Okay, now what we'll do, the exercise, is we know that these errors are actually associated with the existence of either module A or module B. And as we know, it's 13.55 bits if we don't make use of that information. Basically saying module A and module B have nothing to do with the problem. We have the same statistics regardless of the presence of module A or module B. Now, if you make use of module A, essentially what you're saying is the statistics are different for module A being present and module A being not present. So you compress all the reports with A, and there are 3 out of 6 1s, so you need 7.1 bits. And the ones without A also need 7.1 bits. And in particular, you have to add one more bit, because your description of the world, your explanation, has to conclude the information that module A or module B is responsible. So it's 1 out of 2, so you need one more bit. And that's a total of 15.26 bits, which is surprisingly larger than the 13.55 bits you have up there. So you basically can say module A has nothing to do with the problem. We knew this before, but here's basically the mathematics that tell you that's the case. Now, you can try this for now the case of module B, which has 4 out of 6. And if you do the same math, it turns out you still end up with a number of bits that's higher than the 13.55. So there you could say, no, this is actually still chance. It could be chance. It's not a good explanation that module B is responsible. Now, if you had another module C, where that's even more tilted in favor of having the problem, so you have 5 times out of 6, you actually have the problem, and only 1 times out of 6 you don't, or 1 times out of 6 in the reports that don't have the problem, only 1 out of 6 has that module, and 5 out of 6 in the case when module C is present has the problem. In that case, the number of bits is actually lower than treating them all equal, saying the modules have no bearing. The number of bits we have to add now is larger because we have now 3 choices to make. We say A, B, C. And of course, the more hypotheses you have, what could be responsible for the problem, the larger that number gets. And that's the old problem of statistics. If you have the old p-test in statistics, then that everything that's basically less likely than 5% is significant. Then if you have 20 such tests, then one of them will just pass by chance, and you've proven that cucumbers cure cancer. And it's the same thing here. So the more hypotheses you have, the more bits you have to add, and the more significant your signal has to be, so you can still pull it out and say, yep, I found it. I think I found the problem. The math actually is the same if the module fixes the problem. If there's one particular module that makes the problem disappear, you will find it in exactly the same way, no difference. And we extended it to many different hypotheses. So there's hypotheses for modules, for version ranges of modules. So we at the end can say, okay, there is this particular module from this range to that range that is very highly associated with the problem. and that's automatically going to be spit out by our error module, by our error analysis. Okay, there's coming to the end. There's one last thing I want to talk about briefly is the C++ contracts. It's not in the standard. It got tossed out of the standard, and it's a new language feature. It's essentially an assert on steroids. That where you could say declaratively the preconditions, postconditions of a function, and assert you have a new syntax. The problem, of course, is you have to exactly answer the questions that we discussed now here in the talk. So you have to say, when would you actually check this contract? Would you check it only in debug? Would you check it in release? Would you check it never? So that is only documentation for the reader of the code. What do you do if the contract is violated? Do you terminate the program? Do you just carry on? And if you probably want to report to somewhere, what do you report? To where? How do you do this? All these questions are quite complex. This is a big topic, and that's why it got removed from C++20 at the very last moment. So, but I think the discussion will continue for C++23, and it will be interesting what they actually come up with. All right, thank you very much. Yes, we are recruiting. Here's our HR think cell. It's all advertising, of course, always. Yeah, I'm happy if you have any questions.
In order to apply the compression algorithm, you need to associate which cases apply to the same problem. To the same error. You need to associate which cases apply to the same error. Are you able to do this via the dump files, or are they reported in a more complicated way?
No, we do this with a dump file. So usually an error category is a location in the code. We have a few things. We have a list of it works by you receive the dump, you essentially get the stack trace out, and then we have a list of things where you would pop the stack. So, for example, if you have a dereferencing operation, and we have an assertion in the dereferencing operation that what you're dereferencing is not null, then if something if this precondition that what you're getting is not null, it's violated, you probably want to go one higher in the stack, because the problem is not in the function itself, it's in the caller. And so you essentially have a list of functions where you say, okay, if you encounter these list of functions, you pop up. And then that location in the caller would be the location that is actually going into the database. And so that may happen recursively or iteratively. So you may pop up like maybe 1, 2 places in the call stack, and then that's your location. And then you say, okay, this is the problem or the bug location. And anything that happens at that particular bug location, I'm going to categorize as a single error and put it into the database. That's happening. That's working quite well. It's practical. It's fine. And the category is always like function plus line offset. So of course you don't pick line in the source code that changes around too much. You just function plus line offset, and that's something you can get. That works well.
And do you have any automation on that, on the processing of the dump file, or is it?
Say again.
Do you have any automation on the processing of the dump file, or is it a manual process?
The size, or?
I mean, in order to analyze the dump, the process that you just described, do you have any automated way to do this?
Oh, you mean debug symbols?
Yeah.
Yes, I mean, we do have, so Microsoft doesn't provide debug symbols for Office. They do provide them for Windows, and then we do download them. But of course we have, particularly for our code, we have debug symbols. So you have a whole database with all your debug symbols that you can then load into the debugger. It's WinDebug for Windows, and it's LLDB for Mac, where we do the analysis. And we do them for Mac and for Windows. We actually have our own little mini dump facility for Mac. So Microsoft provides one out of the box, but Mac doesn't. But it's not too hard. If anyone is interested, we can certainly share the code. How to get basically something equivalent to the mini dump on the Mac. So you have something like 100 kilobyte or something that you can easily send somewhere.
Hi. You mentioned untested errors. Categories of errors, untested errors.
Untested errors.
Mm-hmm. And you said the problem was being able to reproduce those errors. If you can't reproduce them, you can't test them. Do you ever consider mocking to cover the mocking? Do you ever consider using mocking to?
I mean, I think you could have any sort of automated tests. We could do mocking. We could do all kinds of unit tests. The thing is that most of these errors, if they're not reproducible, have something to do with the environment. It's these unknown problems where you are just not expecting anyone to have a particular configuration of hardware, of software, of other add-ins, and we are in a particularly hard environment because it's PowerPoint, and everyone is writing add-ins for PowerPoint, and things go haywire all the time. Like there's a particular code, like Windows subclassing. Everyone is subclassing Windows, and we actually have code that for add-ins that try to subclass Windows to do it in the right way, kind of rewire them automatically to subclass Windows, because it's such a frequent error that we basically had to overcome this automatically without teaching everyone how to write proper subclassing in their add-ins. So that's why it's an interesting environment, because it's such a uncontrolled environment. Everyone is playing in the same address space. Everyone is writing on top of each other. It's a bit crazy, and that's why it makes for an interesting it's an interesting exercise to make such a program truly reliable.
As you said that the assertions are actually not throwing, so it's not a basic assertion. So I assume you have your own library that is deciding, like, is this assertion going to do reports, and is it going to have like you said, a throtter? Like, because maybe you have some assertion where you are going to say, I want it to send a report only once every, I don't know, 7.
Right. It's our own library. Yes. I mean, there's an infrastructure, error reporting infrastructure. It's actually tiered. So you have one general error reporting infrastructure, and then there is the back end that we're just basically doing the reporting. So there's one that says, okay, we have to throttle, and we have to, actually no, this one actually does. Okay, how do we report certain types of error? If you have a get lost error, API error failing, how do you report that? How it puts together an error string that is more general. And then you can send that basically to your backend, which is either essentially the client backend that has to do throttling, and it has to do, doing the HTTP call request to post your error information, or it's the backend for the server that holds the thread. So you have these kind of two parts of error handling.
So from the client side, you actually have like a process that is going to do that on the side, or you are doing it asynchronously, or it's actually synchronous when you have the assertion that is failing? And there's another application. So it's another application that gets invoked, which is actually then sending the error. And it's the same one that's then doing the update. So if you receive a new binary back, there's actually special code that because the errors happen often during startup, especially if incompatibilities with something, and then when PowerPoint or the add-in hasn't come up yet, that the user cannot lose any data. So you can just silently terminate PowerPoint, install the update, and then restart PowerPoint. So there's a particular state where you can say, well, this is like the checkpoint. Up from here onwards, we don't just terminate. Because user may lose data, but up to a certain point, you can be pretty sure that that's not going to happen because the program hasn't gone to that point, to the part of where it's becoming interactive yet. So there you can still just cut it and terminate it, and then the user won't notice. You would just start PowerPoint, bloop, goes black, installing, PowerPoint back up, and off you go.